Most people first meet linear algebra as a page full of symbols. Vectors stacked into columns, matrices filled with numbers, rules for multiplying rows and columns. It can feel mechanical. But the real subject is much more visual. Linear algebra is the language of space. A vector is a direction with a length. A matrix is a way to move, stretch, rotate, shear, or flatten space. A system of equations asks whether a target point can be reached. A decomposition asks whether a complicated transformation can be broken into simpler moves. In this series, we will build linear algebra from that geometric picture. The goal is not to avoid formulas. The goal is to make every formula point to something you can see. Let us start with a vector. In coordinates, a vector might look like two numbers, 3 and 2. But geometrically, those numbers describe a move. 3 units in one direction, and 2 units in another. You can draw that move as an arrow from the origin to a point. But the arrow does not have to start at the origin. The same vector can be copied anywhere in space. What matters is the displacement. How far, and in what direction. This is the first shift in perspective. The numbers are not the object itself. They are a description of the object measured against a coordinate system. To turn a vector into numbers, we need a basis. A basis is a set of reference directions. In the ordinary plane, we often use one horizontal direction and one vertical direction. If a vector is 3 steps along the first direction and 2 steps along the second, we write its coordinates as 3, 2. But the same geometric vector can have different coordinates if we choose a different basis. Tilt the coordinate grid or stretch one reference direction, and the numbers change. That is why coordinates are not absolute. They are measurements made with a chosen set of rulers. Much of linear algebra is about choosing the right rulers for the problem. Once we have directions, we can scale them and add them. Take one vector v, multiply it by a number, and you move farther or shorter along that direction. Take another vector w, scale it 2, and add the 2 moves together. The result is called a linear combination. If you allow all possible choices of the numbers a and b, you get the span of those vectors. 2 independent directions in the plane span the whole plane. 2 directions that point along the same line only span that line. This idea appears everywhere. Reachable points, possible outputs, data subspaces, and solution sets all begin with span. Now we can introduce matrices. A matrix is often taught as a rectangular table of numbers, but geometrically, a matrix is a transformation of space. To understand a 2x2 matrix, watch what it does to the 2 basis vectors. The first column tells you where the first basis vector lands. The second column tells you where the second basis vector lands. Once those 2 landing positions are known, every other vector follows automatically. Why? Because every vector is a linear combination of the basis vectors, and a linear transformation preserves that structure. So a matrix is not just multiplying numbers. It is moving the coordinate grid in a controlled way. This gives matrix vector multiplication a simple meaning. When we write ax, we are sending the vector x through the transformation A. Suppose x is made from 2 parts, c1 times the first basis vector, plus c2 times the second basis vector. After the transformation, the coefficients stay the same, but the basis vectors have moved. So ax is the same recipe, rebuilt from the transformed basis directions. This is the reason matrix multiplication works the way it does. The columns of the matrix are not random. They are the new positions of the basis directions. Once we see a matrix as a space transformation, several important ideas become visual. The determinant tells us how area or volume changes. A determinant of 2 means areas double. A negative determinant means orientation flips. A determinant of 0 means the space has been flattened. Rank tells us how many independent dimensions survive the transformation. A full rank transformation keeps the plane two-dimensional. A rank 1 transformation crushes the plane onto a line. And an inverse matrix exists only when the transformation has not destroyed information. If space is flattened, many different inputs land in the same place, and there is no unique way to reverse the move. This also changes how we read a system of linear equations. The equation ax equals b is asking a geometric question. Is there an input vector x that the transformation A sends to the target vector B? The set of all possible outputs is called the column space of A. If B lies in that space, the system has at least one solution. If B lies outside it, the exact system has no solution. Later, when exact solutions do not exist, we will use projection to find the closest reachable point. That is the geometric heart of least squares. From here, the rest of linear algebra becomes a connected map. Dot products let us measure angles and lengths. Orthogonality lets us split a vector into useful pieces. Projection finds the closest point in a subspace. Eigenvectors reveal directions that a transformation does not rotate away from. Diagonalization and matrix powers become simple when we choose those directions as coordinates. Singular value decomposition shows that any matrix can be understood as rotation, stretching, and another rotation. Principal component analysis uses the same geometry to find the main directions in a cloud of data. Even optimization, Fourier transforms, and kernel methods will fit into this same picture. Here is the main idea to carry forward. Vectors are geometric objects. Coordinates are how we describe them using a chosen basis. Matrices transform the whole space by moving the basis directions. And equations like ax equals b ask whether a target point can be reached by that transformation. If you keep that picture in mind, the formulas will start to feel much less arbitrary. In the next episode, we will slow down and focus on vectors, bases, and coordinates. That is where the geometry of linear algebra really begins.